Welcome back to Honors Calculus. In this video, we're going to be looking at the intermediate value theorem. The intermediate value theorem is a tool we can use to codify what is one of the most important aspects of a continuous function. Uh, Prior to studying calculus, you understood the idea of a continuous function as a function whose graph you could draw without lifting your pencil. We created a mathematical basis, a more concrete tool we could use for studying that idea of a continuous function. But now we want to tie it back to what the picture looks like. And that's where the intermediate value theorem is going to come in. The intermediate value theorem is sometimes called one of the big three theorems in calculus. The intermediate value theorem, the extreme value theorem, and the mean value theorem together. And they're called the big three theorems because they are theorems. They involve quite a bit of effort in order to prove them. And the proof is going to rely on the completeness axiom that we talked about previously. So without further ado, let me get my head out of the way and let's get started. It turns out that the intermediate value theorem itself is not something we can dive straight into. So we take an intermediate step of the intermediate value theorem. Looking at what's called Bolzano's theorem, named after the mathematician Bolzano. Consider a function f, which is continuous on the closed interval from a to b. F of a is less than 0, f of b is greater than 0. Bolzano's theorem claims that there exists a value c somewhere in that interval such that f of c is actually equal to 0. Before I get into the proof, I want to take a aside here really quickly and look at continuous on the closed interval from a to b. We know the definition for continuous at a point. The function exists, the limit exists, and the limit gives you the value of the function. We can extend that to continuous on an open interval if the function is continuous at every point in that interval. Continuous on the closed interval is a little bit trickier. To be continuous on a closed interval, well, continuous on the open interval we've just established is pretty straightforward. But the endpoints are the tricky thing because the limit isn't defined necessarily on an endpoint. And so to establish what's happening at the endpoints, we use one-sided limits. Actually, I guess I have to put this. All right. So the idea here of continuous on the closed interval, we're allowed to have a jump discontinuity or any kind of discontinuity at the endpoint, as long as the value of the function agrees with what is happening, right? The jump has to happen after that point. So closed on the interval from A to B, and then open going beyond is how the piecewise function would have to be set up for that to work out. Right. And this picture also is telling us pretty nicely what's happening. The claim here is that if you have a curve which is below the x-axis on one side and above the x-axis on the other side, and it's continuous, the only way that can happen is if there is some point in the middle, we'll call that point C, where the graph goes right through the x-axis. And before I get into trying to figure out that C exists, I also want to point out here that this theorem tells us that the point C exists. There is a point where this happens. It doesn't tell us that there's only one point where this happens. This function could do some crazy sinusoidal thing where it crosses the x-axis many, many times. There's nothing wrong with that. There's nothing stopping that from happening in this theorem. All we know is that it has to cross at least one time. And here again is why proofs can be so useful, because our proof is actually going to give us uh, excuse me, our proof is actually going to give us something of a structure that will help us identify where this point C might be located. So let's take our set S. We're just going to invent a set S. It's going to be a subset of the interval we care about. And it's specifically going to be the elements in that set where when we evaluate the function, we get something less than 0. So if we look at the yellow curve up here, it's going to be all of these values. If we look at the blue curve, it's going to be this bit, and that bit, and that bit, and that bit. One of those things has to happen. Now, AB is a bounded interval. The interval between A and B is bounded. That, nothing outlandish there. And since S is the set of all things in A and B, it must be that, why did I write AB again? Sorry about that. It must be that S itself is a bounded set, right? A is a lower bound of S. B is an upper bound of S. They may or may not be the greatest lower bound and the least upper bound, but they are lower bound and upper bound nonetheless. Now, an interval is a subset of the real numbers, and a subset of a subset is a subset of the original set. So S is a subset of the real numbers, and the real numbers are complete. With those two facts, the least upper bound of S exists. It might be B, it might not be, but it does exist, and that's all that matters. If f of c is equal to 0, then we're done. That's pretty easy. Right? I don't remember if I've used a Woolog statement here or not. WLOG, often pronounced as Woolog, stands for without loss of generality. I'm making an assumption. There is nothing that says that this assumption must happen. The claim of a Woolog statement is that if I made the opposite assumption, the proof would still work basically the same. Right? If f of x is not in fact greater than 0, we can define g of x as the opposite of f of x, and then g of x will be greater than 0. We'll have a new function to work with, and we can follow the same process as before. Now here's where things get really tricky. Right? We're going to try to use every single thing that we know about this function, and we know a decent bit, right? We know that the function is continuous. We know that f of a is negative, f of b is positive. We looked at just the parts which were negative, and we know that there's at least one thing there, because at least the value a itself is in S. And so we used the fact that we had some negative and positive to get this thing. We found this particular value c. It might not be the c that we care about. We also know that the function is continuous at c because it's continuous everywhere on the interval ab. So the definition of continuity shows up. Right? Now we've written down the limit. And when we write down a limit, we can think about epsilons and deltas. So let's pick some values of epsilon. All right, I'm going to pick epsilon is f of c over 2. Why am I picking that? Because black magic. I went off to the side earlier and I did this whole proof and I figured out what the result needed to be for things to work out nicely. So I pick epsilon as f of c over 2. Right, here again, we've figured out that f of c is bigger than 0. If it's not, then we pick epsilon to be the opposite of f of c over 2, and everything works out fine. Right? By definition of the limit, it must be that there exists some delta greater than 0 such that when 0 is less than the absolute value of x minus c is less than delta, it is the case that the absolute value of f of x minus f of c is less than epsilon, which is f of c over 2. Right? We've got some absolute value inequalities going on here. And whenever we have absolute value inequalities going on, one of the things we can do is expand them out. So we have absolute value of x minus c is less than delta, which means that the opposite of delta is less than x minus c is less than delta itself. So c minus delta is less than x is less than c plus delta. Same thing with the other absolute value inequality. Absolute value of f of x minus f of c is less than f of c over 2, which means that the opposite of f of c over 2 is less than f of x minus f of c is less than f of c over 2. Adding f of c to all three sides of this inequality gives me that 1/2 f of c is less than f of x is less than 3/2 f of c. All right, now we get to the interesting bits. Over here, we have a range below and above the value of c. And right behind me, we have f of x, which is always positive. All right, that doesn't seem like too big of a deal here. But watch. If I plug in that x is equal to c minus delta, I get that 1/2 f of c is less than f of c minus delta is less than 3/2 f of c. But when I picked f of c, I specifically picked because f of c over 2, 1/2 f of c is bigger than 0. C was picked as the least upper bound of the set of functions f of x, or the set of values of x, so that f of x is less than or equal to 0. C minus delta, something smaller than C. Everything between C minus delta and C also has this behavior of being greater than 0. So C minus delta should also satisfy and be an upper bound for the set of f of x less than or equal to 0. But it's smaller than the least upper bound. It can't be an upper bound smaller than the least upper bound, or the thing we call the least upper bound isn't actually the least upper bound, but we said it was the least upper bound, so we must have been lying. Well, the only assumption we made was that the least upper bound f of c was greater than 0. And I said that if we had found that f of c is less than 0, we could have gone through and done the exact same proof. And we'd have gotten that c plus delta is also a greatest, or also a least upper bound, and still would have come across the same circumstance. This technique used here is called a proof by contradiction. Proof by contradictions can be a little bit difficult to digest at first glance. We rely on coming up with something nonsensical, and the nonsense is often incredibly subtle. I don't necessarily expect that you can reproduce this proof. I certainly don't expect that you can write your own proof by contradiction coming out of this course. But I do expect that you can follow the logic and understand step by step that everything I said in this proof is true. And you can accept, it makes sense, Bolzano's theorem itself. If you have one side lower than the x-axis and the other side above the x-axis, the only way to get from here to there is to either have a discontinuity or to cross the x-axis. Proving that is not straightforward, as we just saw, but the idea itself makes a lot of sense. And now that we have that idea, we can go onward and get to the intermediate value theorem itself. The intermediate value theorem, if you thought Bolzano's theorem looked messy, this thing is a nightmare. Let f, mapping from the real numbers to the real numbers, be a function which is continuous on the closed interval from a to b, and let k be somewhere strictly between f of a and f of b. Then there must be some value c in the open interval from a to b such that f of c is equal to k. The statement of this theorem looks quite a bit messier, although the proof is going to be quite a bit easier. But first, let's take a look at this phrasing right here. Let K be strictly between f of A and f of B. This phrasing is awkward because we don't know which one is bigger, f of A or f of B. But with this phrasing, we know it has to be strict inequality. They can't be equal to each other. And we know that K has to be somewhere in between. So either f of A is less than K is less than f of B, or f of B is less than K is less than f of A. One of those things has to be true. That's what we mean when we say K is strictly between f of A and f of B. And that's going to be our starting point for our proof. If we have the first option, f of A is less than K is less than f of B, notice that if I subtract K from all three sides of this inequality, I will get f of A minus K is less than 0 is less than f of B minus K. And so I'll define g of x equals f of x minus k. If I have the other possibility, if it is the case that f of b is less than k is less than f of a, I'm going to take the negative here, and I'll get that the opposite of f of a is less than the opposite of k is less than the opposite of f of b, and then I'll add k to all three sides of this inequality, and I'll get that k minus f of a is less than 0 is less than k minus f of b. Here I have k minus my function, so I define g of x equals k minus f of x. And notice that no matter which of these definitions of g I pick, if g of x, or I'm sorry, if g of c is equal to 0, then f of c is equal to k. And the way that I structured this value of g of x means that Bolzano's theorem is satisfied. We have a negative on one side, we have a positive on the other side. We are looking for 0 somewhere in the middle. Bolzano's theorem tells us we can find it. Doesn't tell us anything about where we can find it, but it tells us we can find it, and that's good enough for us. There are a number of applications in calculus for the intermediate value theorem. Outside of the study of pure mathematics for its own sake, The intermediate value theorem is also very important in numerical analysis because it guarantees that the binary search algorithm will work. All right, so I'm going to pick specifically that f of a is less than k is less than f of b, but if this went the other way, the idea would still work. We're looking for that point. All right, so we have our graph, which is doing its thing. We have a point that we care about, and we're trying to figure out when that thing happens. Applications here range as wide as you're tracking the motion of an object, a ship, a particle, whatever, and you want to know when it is going to be at the particular place that you care about. So you have a function mapping where it is going to be at every point in time, and you're looking for the time where it does the interesting thing. I know I'm being very vague because this is math class, and I don't want to get bogged down in the details of the system in question. Instead, I want to focus on the application here. We'll use this process. If f of c1 is equal to k, we're done. If f of c1 is less than or greater than k, we're going to make c1 the new value of b. If f of c1 is less than k, we're going to make c1 the new value of a. And then we're going to do the whole thing again. We'll find c2, c3, and we'll keep going until we get to what we looked for. Now, in computer science, equals is a bit of a problem because you can have some really ugly irrational numbers and you'll never get there. So generally there's a fudge factor thrown in for good measure, but we're going to look at a particular example that works out pretty nicely, and so we don't have to worry about it. I'm going to look at the function f of x equals x squared for x in the interval from 1 to 5. I'm going to look for f of c such that, or I guess I'm going to look for c such that f of c is equal to 6.25. All right, so we'll pick C1 is B, which is 5, minus A, which is 1. I'm sorry, plus A, which is 1, all over 2. 5 plus 1 is 6. 6 over 2 is 3. F of 3, 3 squared is 9, which is bigger than 6.25. So now we don't have to look at the entire region from 1 to 5. We can look at the region. Lower bound stays the same because we had greater than here. Our upper bound is going to change to the value of c we picked before. And so we can find c2. And if that works, we're great. If not, we'll go on to find c3, and we'll see how many steps it has to take. right? You are not a computer, you're also not a computer programmer, so I don't expect you to do this in any great depth uh, by hand, and I don't expect you to write a program to do it for you. I will promise you that if I ask you a question like this, you can resolve it in 2 or 3, 4 at the most steps. More than that is just ludicrous. But I would like you to try to finish this one off. Using the process that we had, we just found the interval narrowed from 1 to 5 down to 1 to 3. You can narrow it down further, you can narrow it down further, and hopefully you eventually get the value that we care about. So see what you can do with that, and I'll see you in the next video.